Morning all. Sorry I'm late.
Morning.
Having a login issue, but it's obviously resolved now. All right. I'm going to continue with what we were doing. I guess we've just gotten through with molecular orbitals. I'm thinking. I'm just trying to remember. See, I'm teaching some of the same stuff in my Chem 2 class, and sometimes I get a bit confused about which one I'm actually doing at the time. But let's have a look. Okay. Yeah, we were working on MO theory, phases of matter. I think we got through that too. Intermolecular forces, right? Okay. Yes, we got to intermolecular forces. I remember now. All right. Solubility of gases and liquids. This won't be on the test. There is a fun quiz about it though, and if you want to read about that here, you can. I'm not going to cover it because you can read it here on the slide, and then you can go ahead and do the quiz. So there's a quiz. It's in the. Oh, well, let me see what folder it's in here, so I can direct you to it. Let's have a look. I think it's under intermolecular forces or colligative properties. Nope, it's not under intermolecular forces. It must be under colligative properties. There it is. Yeah, so it's under colligative properties, solubility of gases in liquids. That's what that quiz is about. Like I said, it's not on the test though, so I'm not going to bother covering it. If you want to read about it, you can here. There's an example there as well. It's pretty much set up the way that the quiz is set up. All right, so what we're going to work on now will be concentration and colligative properties. So concentration, let's close that down. We don't need that. Okay. It's an amount of solute, specifically in an amount of solvent or solution. All right, so let's look at the definition of those three things here. I think I've been through this before, but I'm going to go through it again because I think it's worthwhile. So we've got our solute here. That's what's going to be dissolved. And then down here, you've got the solvent. That's going to do the dissolving. And then once those things have been added together and the solute has been dissolved, then we get what's called a solution. So that's going to be the combination of the solvent and the solute. So I'm actually going to put that in here. Solute plus solvent. So as you can see, in my definition of concentration here, it's always a solute that's on top. It's an amount. It could be any amount that we're talking about here. It could be moles, could be grams. There's lots of different things that could be. And then on the bottom, we have either the amount of solvent or the amount of solution. It depends on the concentration unit that we're actually talking about. There's another thing to consider as well, and that's the effect of a solute on the volume of the solution. So if this is a solid solute, I'm going to make a big deal about this because we do handle these things a little bit differently. A solid solute, you stick it in and you'll notice that there's really no appreciable change, no significant change in solution volume. So I'll give you an example. If you were to take an Alka-Seltzer and put it into water, you'll notice that the volume of the water doesn't change much, and that's important. No significant change in solution volume. So let's look at another example. Let's say we've got a liquid solute. And I'm going to give you clues as to how you can tell if something's a liquid or a solid. It's going to be obvious. But you'll notice that the volume will change. And the volume of the solution is going to equal the volume of the solvent plus the volume of the solute. So hopefully you can see the difference between those two situations. So what we're going to do is I'm going to show you an example that is going to be 4 different kinds of concentration measurements and calculations. One will be done as a solid solute and the other one will be done as a liquid solute. What you'll see is that only molarity is the one that ends up being affected by this fact that we have a solid solute or a liquid solute. All the other concentration measurements or calculations are not really affected by this, but I'm going to make a big deal of that when we get to molarity. So the 4 kinds of concentrations we're going to consider are going to be percent by weight, molarity, molality, and mole fraction. Okay, so we're going to start. Here's the example for a mixture of 22 grams of phenol, and here I even tell you it's a solid, so we are dealing with solid solute here. I give you the molecular formula, which allows you to get the molecular weight, and I also say what it's dissolved in. Now, I think it's really useful to be able to determine what the solute and the solvent is just by looking at the question. There's a couple of clues to this. The first thing is that the sheer amount of the substances involved is going to give you a big clue. So the one that has a huge amount or a much larger amount than the other is generally going to be the solvent. Well, it always will be the solvent. The smaller one obviously will be the solute. The other thing that's important is that concentration is always talking about the solute. Everything is about the solute. When we're talking about the concentration of something, it's whatever is dissolving. So it's a solute that's important. So when I say percent by weight of phenol, you automatically know, oh, that's a solute. Molarity of phenol, oh, that's a solute. Molality of phenol, yes, that's a solute. So whatever the question is being asked about, that's also the solute. Does anybody have any questions so far? How do you feel so far about this? How do you feel so far? 5, 4, 3, 2, 1. Okay. Most people feel pretty good. Does anybody have any questions? Do we have any questions? Okay. So the first one we're looking at here is the percent of solute, or phenol in this instance, and the percent of phenol is going to be 22 grams divided by 22 grams plus 160 grams. So it's the mass of the solute plus the mass of the solvent. Another way of expressing that would be to say the mass of the solution, which is going to be both components. Multiply that by 100%. Now, percentage is always part divided by whole. It's like if I wanted to figure out the percentage of females who are on the call, I would count up the number of females and divide that by the total number of people in the class. That would give me the percentage. Multiply that by 100%, of course. The sig figs here, we've got 2 sig figs on top, and then when we add these together, that's actually 3 sig figs because this is addition down here. So that'd be 182 grams, which would be 3 sig figs. But then when we divide, it becomes 2 sig figs, so it'd be 12%. Does anybody have any questions about percent by weight? Any questions about percent by weight? Okay. Now, molarity. This one's important. See, it's moles of solute over liters of solution, and that's the key word, is solution. So as you can see, this is the one that gets affected depending upon whether you have a solid solute or a liquid solute. In this specific example, I'm telling you, you have a solid solute. That means there's going to be no significant change in the solution volume, which means that effectively the volume of the solution, or the volume of this, yes, volume of solution equals the volume of solvent. That's it. Let's try it again. Solvent. Does anybody have any questions? All right, so let's look at how you might do that. First of all, you need the moles. To get the moles, what we do is we multiply by 1 mole over 94.00 grams. Now we get that from the molecular formula, which is given here. So it's a matter of just adding those up from the periodic table. 6 carbons, that's about 72, 6 times 12, plus 6 for 6 hydrogens, it's about 78. And then plus 16, that'd be about 94. So that's how I'm getting the 94 out of that. We do the math on this and it comes out to be 0.23 moles. Does anybody have any questions so far about getting the moles of solute? Okay. This next part is a little tricky. It's about getting the volume of the acetic acid. As I said, since it's a solid solute, the volume of the solution is the volume of the solvent, and what we're looking for here specifically is liters of solution. And what we need to do here is we need to figure out a volume of acetic acid, but what we have is the mass. The other thing we're given in the problem is a density of acetic acid, and I've given it here as 0.800 grams per mil. So the formulas that are going to be necessary for you to be aware of here, of course, the density formulas. So the density is equal to mass divided by volume. That means that mass is equal to density times volume. And we also know that volume is equal to mass divided by density, or it also equals mass times 1 over density. So when you're looking at how I'm calculating the liters here based on the mass, what I do is I take the 160 grams, I multiply it by 1 mil over 0.800 grams. That is the flip of the density. So effectively, by multiplying by the flip of the density, which is 0.800 grams per mil, I'm just flipping it here, the grams will cancel. I'll be left with mils, which then can then be converted into liters. We do times 1 liter over 1,000 mils. That gives us 0.200 liters. So I take those two and I divide them into each other, the moles divided by the volume, and that gives me the molarity. The molarity, big M, is equivalent to moles per liter. Does anybody have any questions?
Why would we flip it?
I beg your pardon? Sorry?
Why would we flip it?
Well, we need mass divided by density, right? To
Yeah.
get the volume. So to divide by density, that's 1 over density. 1 over density is the flip of density. It's the inverse.
Oh, okay.
If you were to multiply density and volume, for example, what you get is mass. We don't need that. We have mass, we need volume.
Thank you.
We did something similar to this back in module 10 when we flipped the concentration. You know, we were looking to get a volume out of that. And that was something we had to do there as well.
Thank you.
All right, no worries. Does anybody have any other questions? All right, how do you feel about molarity? How do you feel about molarity? Five, four, three, two, one. All right, so most people are on board. Does anybody have any questions? Okay. Next one is one you're probably not familiar with, and that's molality. Now, molality specifically is moles of solute over kilograms of solvent, and it's really important that you're aware of that distinction, because molarity was moles of solute over liters of solution. If you remember, the solution is the solvent plus the solute. In this case, molality is just moles of solute over kilograms of strictly the solvent. So down here, it's this top one, amount of solvent here specifically. Now the moles of solute we've already got. We got that previously up here, 0.23 moles. So we're using that same value. And we need the mass of the acetic acid, but it needs to be converted into kilograms. So it's 160 grams divided by times 1 kilogram over 1,000 grams. That gives me 0.160 kilograms. We divide the two and we get 1.4. And the unit there is little m, and little m is equivalent to moles per kilogram. So big M is molarity, moles per liter, and little m is moles per kilogram. So about what we're doing here, the reason that we might use molality over molarity in certain circumstances is that liters of solution or volume can change depending on the temperature. I think most people are aware that when we heat a liquid, it expands, and when we cool it, it contracts. That changes the volume. But what the temperature doesn't change is the mass of the solvent. Right, so temperature doesn't change the mass of the solvent. So molality is often used in applications where temperature is important. And one of those will be when we're considering boiling points and melting points. You know, we're freezing and boiling stuff. That's when molality is really going to matter. And I'll show you examples of that in a little bit. All right, how do people feel about molality? This one is a new one. How do you feel about molality? 5, 4, 3, 2, 1, 0. Okay, most people still feel pretty good about it. Does anybody have any questions though about molality? A couple of people understood, said they understood it halfway. Any questions? Okay. The last one is called mole fraction, and you look at it, it does look a bit similar to percent by weight if you really sort of squint. Now, mole fraction is strictly a fraction. It's not a percentage, it's not a mole percent, it's a mole fraction. If you want the mole fraction of the solute, in this case, the phenol, it would be the moles of phenol divided by the moles of phenol plus the moles of acetic acid. So it does look pretty similar back up here to the percent, but we're not multiplying by 100%. That's why we don't have a percent at the end. But you'll notice that it is moles divided by moles, which means there's no unit on it. The symbol for mole fraction is this Greek letter chi, C-H-I, chi. And for chi of phenol, or the mole fraction of phenol, is going to be 0.23 moles divided by 0.23 moles plus 2.67 moles. The 2.67 moles comes from taking the mass of acetic acid and multiplying by 1 mole over 60.00 grams, which is the molecular weight. We get the molecular weight by using the molecular formula here. 2 times 12 is 24, plus 4 is 28, plus 32 is about 60. So that's why I'm getting 60 for the molecular weight of acetic acid. After we do that, it comes out to be 0.079. The number of sig figs here is going to be 2 because of the 0.23 divided by whatever this adds up to, which would be about 2.90 down the bottom. So it'd be 2 sig figs divided by 3 sig figs, and we get 0.079. To get the mole fraction of acetic acid, we can do exactly the same thing, just put the moles of acetic acid on top. We get 0.921, but if you look at those two, you'll notice something about them. And that is that when you add them together, they come up to 1, which makes sense because mole fractions are going to be fractions of what's involved. So adding the two together should give 1. This gives you another way of getting the mole fraction of acetic acid if you really wanted it, and that would be simply by subtracting 0.079 from 1, which would give 0.921 with that same number of significant figures, because it would be going by a number of places past the decimal, because that would be subtraction. We're mostly interested, though, to be honest, in the excuse me. We're mostly interested, though, to be honest, in the mole fraction of the phenol. That's the solute, and most of the time that's what we're going to be engaging in here. Does anybody have any questions about mole fraction? All right. So you'll notice that now I'm going through the same examples again, but this time I'm going to use a liquid solute. Now, liquid solutes are going to be the same kind of calculation for percent by weight, for molality, and for mole fraction, but there will be a difference when we're considering molarity because this depends on the liters of solution. Now, as I was making a big deal of this earlier, I said with solid solutes, there's no real change in the solution volume. The volume of solution essentially equals the volume of solvent. With a liquid solute, however, the volume of solution is going to be the volume of the solvent plus the volume of solute. It gets bigger. So there is a change in the volume of the solution here. And there will be in this instance as well. But going back to the mass percent, so we've got percent by weight of furfural, that's going to be the solute here. And I'm given here a volume of furfural, but I need a mass of that. And the way I get the mass is by using the density. As you can see from the formula down here, mass is density times volume. Remember that volume was mass divided by density. So mass here is density times volume, because I started out with a volume here, which gave me 25 grams of furfural. That's what gets put into the equation here, 25 grams on 25 grams plus 160. And the 160 grams is the grams of ethanol here. That's going to be the solvent. And now we need to calculate that concentration. It comes out to be 14%. All right. How do you feel about the percent by weight here? How do you feel about this percent by weight? 5, 4, 3, 2, 1, 0. Some of you are a bit slow on the vote here. Okay, does anybody have any questions? All right, so this is the one that changes. This is the molarity of furfural. This was a bit different to the previous one. We do something similar at the beginning. We need to find the moles, so we take the mass that we got in the previous part of the problem up here. By taking the density multiplied by the volume, that gives us the mass of the solute, which gets converted into moles of solute, and we use for that, of course, the molecular formula, which is given up here, C5H6O2. We need liters of solution. Now, for that, we need the volume of ethanol, which we can get again by taking the mass and dividing it by the density, which is times 1 over 1 mil over 1 over the density, which is times 1 mil over 0.789 grams, which gives us those milliliters. We already have the volume of the solute. We add those two together and multiply by 1 liter over 1,000 mils, which gives us 0.225 liters. We take the 0.25 moles that we got up here, divide by the total volume of both of them. Now, I want to really highlight the distinction between that and what we did previously. So in the case of molarity of phenol, which was a solid, you'll notice all we did was that we found the volume of the solvent, which was the acetic acid, but that was it. which is used that as liters, and that became the liters of solution. In the case of the liquid though, it was a little bit different. We had to add the two volumes together, and that gave us 22 mils plus 203 mils, which needed to then be converted into liters, which gave us the molarity. So it's a little bit different from the previous one. This is the only one that changes depending upon the kind of solvent you're dealing with. Solvent, the kind of solute you're dealing with, whether it's a liquid or a solid. All right, let's see. How do you feel about this molarity here? How do you feel about the molarity? Five, four, three, two, one. Okay. Does anybody have any questions? The molality of furfural is just going to be moles of solute divided by kilograms of solvent. And again, it's just the solvent, not the solution here. So we're only interested in the mass of the solvent in kilograms, which is that same conversion as we did earlier. We take 160 grams, multiply by 1 kilogram over 1,000 grams, 0.160 kilograms. The molality then is just going to be the moles that we picked up from up here in the second part. And then that's going to be divided by the mass of solvent in kilograms. Does anybody have any questions? The mole fraction is exactly the same as it was before as well. We need to get the moles of each. We already have the moles of furfural. Now we need the moles of ethanol. And that would be 160 grams times 1 mole over 46.07 grams, which we get again from the molecular formula, which is up here. Whoops. Molecular formula, which is here, C2H60. We take the moles of furfural divided by the moles of furfural plus the moles of ethanol. That gives the mole fraction, again, no unit. And then the moles of the mole fraction of ethanol would be the moles of ethanol divided by the moles of furfural plus the moles of ethanol again. So adding those two together again gives 1, which allows us to get the mole fraction of ethanol just by subtracting 0.067 from 1 as well. Does anybody have any questions? All right. So that's those are all the concentration units that we're going to talk about. So what are we going to do with these? Well, what we're going to do is we're actually going to apply these to another concept known as colligative properties. Now, colligative properties are such that they are not affected, their properties, but aren't affected by the nature of the particles, but simply by how many particles there are present. So examples of colligative properties include the following: freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So these specific 4 properties of solutions are going to depend entirely on how much we have of something, not what we're actually dissolving as a solute. All right, we'll see how that works in a bit, but what I'm going to do first is explain what each of these colligative properties is in real life. And the first one is freezing point depression. Now, the reason that freezing points get depressed when you put a solute onto a solid substance that is the solvent, what will happen is, for example, if you've got ice, which is solid water, and you put salt on top of it, what will happen is the ice will melt to dissolve whatever you're putting on top of the ice. This is the concept that is taken advantage of during the winter up north when the roads get salted. The idea is that the salt on the ice will cause the ice to melt or freeze really at a lower temperature. So instead of freezing at 0 degrees Celsius, it'll freeze at a lower temperature than that, which means that the water on the road will stay as water longer rather than as ice, which is a lot more dangerous to drive on. So that's the idea. The problem, of course, is that the salt plays havoc with rust and everything else. It's a pretty nasty situation, but it also beats car accidents too. So that's freezing point depression. It will lower the freezing point of the ice, which means that it will just help dissolve. The ice will melt to help dissolve whatever's on top, keeping it in the water phase longer to a lower temperature. In fact, if you have the right ratio, you can lower the temperature of freezing by up to minus 20 degrees Celsius, which is pretty significant. Does anybody have any questions about freezing point depression? The next two are kind of the result of the same thing. We've got boiling point elevation and we've got vapor pressure lowering. So if you have a pure liquid, what will always happen is there'll be liquid in the bottom of the container, and then sitting above the liquid, you'll always have gas molecules of that same liquid, which produces what we call a vapor pressure. Now, we've dealt with this before because we were looking at this back in module 11 when we were doing test 2. So what we find is that we've got the liquid in the bottom, we have the vapor on top. And then if we decide we want to dissolve something in the liquid, some sort of solute, what's going to happen is those gas molecules will come back down into the liquid to help dissolve whatever we've put in the liquid. That's these dots here. All right, so liquid with these dots dissolve. So the X's come back down into the liquid. So this has two effects. The first effect is that it lowers the vapor pressure by lowering the amount of X sitting around above the liquid. That's the first thing. The second thing it does is it raises the boiling point. Now, the reason for that is because now you've got all these X's that were above the solution are now down trying to help dissolve whatever you've put into the liquid. So when you heat the liquid, it takes a little bit more energy, a little bit more heat to get those X's out of the liquid and back into the vapor phase. Once the vapor pressure reaches atmospheric pressure, that's called boiling. That's normal boiling point. That's when the vapor pressure above the liquid equals atmospheric pressure. Obviously, you've seen water boil. You know what it does. It bubbles. And at that point, the vapor pressure above the water is equal to atmospheric pressure. And that's why bubbling occurs. It's all that steam coming out of the water causing those bubbles. Does anybody have any questions about boiling point elevation or vapor pressure lowering? The last colligative property we're going to talk about is called osmotic pressure. Now, osmotic pressure is best described in this fashion here. You can see that there is a U-shaped tube, and down the bottom of this U-shaped tube, we've got what's called a semi-permeable membrane. Now, I know it's a little bit hard to see in this diagram, but there are little things dissolved on this side of the semi-permeable membrane. Now, the semi-permeable membrane is going to allow for free passage of the solvent, but not the solute. So that's the nature of the semi-permeable membrane. An example of semi-permeable membrane is a frog skin. Also, sausage casings, good semi-permeable membranes as well. But as I said, you've got the pure liquid on this side of the semi-permeable membrane. On the other side, you've got liquid with the solute dissolved in it. So what happens is that the solvent will flow from this side, pure solvent, to this side of the semi-permeable membrane. The reason it does that is to help dissolve whatever we've put in there. Now, what happens then is you've got a piston down here. It puts a pressure on that side of the semi-permeable membrane, which pushes the piston upwards. That's called osmotic pressure. And it has the symbol capital Pi. That's the osmotic pressure right there. Does anybody have any questions so far? Some of you in biology might have done an experiment where you took a potato and you take the potato and you stick it into salt water. And what happens is, after you leave it there for a while, what happens is that the potato shrinks, shrivels up. And the reason for that is because this potato's skin is acting as a semi-permeable membrane. And what happens is the pure water that's in the potato leaves the potato and goes out into the salt water to help try and dissolve the salt water. In so doing, though, the potato becomes shriveled. So this kind of thing is used to describe what happens when cells are put into environments where the electrolytic concentration is too high, and what effect that can have on cells. It does have a similar effect. They can act as semi-permeable membranes as well. I mean, you've seen it yourself. If you stick your fingers into salt water, your fingers will wrinkle up pretty quick. All right, does anybody have any questions? All right, let me see how you feel about the colligative properties. We've discussed all 4 of them. How do you feel about them? How do you feel? How do you feel about colligative properties? 5, 4, 3, 2, 1. Okay. Most of you feel pretty good about it. Does anybody have any questions? Okay. So that was my foray into examples of those kinds of colligative properties. But we can take this a step further, and we can actually do calculations that are based on the concentrations that we found earlier, or the concentration units we were just looking at. So for example, if you wanted to find the freezing point of the above solution, now when I say the above solution, what I'm talking about is this one, the phenol in the acetic acid. So we're looking for what happens to that. Now to get that, what we need is, we need to find the delta TF, and we do that by doing delta TF equals KF times M. You did this, oh no you don't, maybe that was Chem 2. You'll do this as in the lab in Chem 2, if you take Chem 2. So delta TF, that's a change in temperature for freezing point, is going to be KF times M. You are given the value of KF, which is called the Molality freezing constant, which has the value 3.90 degrees Celsius per molal, and that's what that little lamb is called. It's also called molal. So let me put that down here. So big M is called molarity, and little m is called molality, but it's also shortened to molal as well. Molarity is shortened to molar. So molar and molal, I know it sounds confusing, I get it. So delta TF is going to be KF times the molality. Now we did get the molality up here. We got it at this point, molality of phenol came out to be 1.4 little m. So what we do is we take the molal freezing constant, which we're given, 3.90 degrees Celsius per molal, multiply it by 1.4 molal, and you'll see that the molals cancel, and we're left with 5.5 degrees Celsius. What does this represent? Well, it represents a change in freezing point. Now, the pure freezing point is also given here in the problem, 16.6 degrees Celsius. There it is right there. So in order to figure out the freezing point, the new freezing point, we take the 16.6 degrees Celsius and minus 5.5 degrees Celsius. And the reason we're subtracting it is due to freezing point depression. That's the thing. When freezing points are affected by solutes, they go down. It's always freezing point depression. So that's why I take the pure value, which was given to me, and minus the change, the delta TF, which is equal to KF times M. That gives us 11.1 degrees Celsius. Does anybody have any questions?
How did you get 1.4 meters?
No, it's not meters, it's molal. It was up here. We got it from this part of the problem. We're talking about this solution here, Michael, the one in the example that we were looking at.
Okay.
And the 1.4 M comes from here, molality.
So it's molality then.
Yes.
All right, thank you.
All right. Does anybody have any questions? Okay. All right, let me see how you feel about it. How do you feel about freezing point depression? 5, 4, 3, 2, 1, 0. Okay, does anybody have any questions? Anybody have any questions? So you can see the results when I share them, right? Is that true?
Yeah.
Yeah, good. So similarly, we can also find the boiling point of the same solution. For this, we use a similar formula, but the Kf and the Kb are different. We're given the molal boiling constant as 3.07 degrees Celsius per molal, along with the boiling point of the pure acetic acid. So one thing you've got to understand here is that, and this sometimes leads to a little bit of confusion, is that the concentrations are all about solute. It's all with respect to the solute, whereas colligative properties are more about the solvent, or more correctly, the solution, I suppose, which does depend upon really both the solvent and the solute. But we're looking for the boiling point of the entire solution, which does depend on the concentration of the solute. So delta TB equals KB times M. And again, it's the same M value as we used earlier, 1.4 M. And we get 4.3 degrees Celsius. This represents a change in boiling point. Now, to get the new boiling point, we don't subtract here, we add, and it's because it's boiling point elevation. So if you think you'd have trouble remembering its freezing point depression and boiling point elevation, one thing you can do is you can say, well, a lot of people get depressed when it's cold. So you can say freezing point depression. And they get excited when it's hot. So it's a boiling point elevation. All right, does anybody have any questions? Any questions about boiling point elevation? Okay, it's pretty much the same as freezing point depression. Now, vapor pressure lowering. Now, these formulas, you don't have to memorize them. They're actually given to you in the test. So this one is about vapor pressure lowering, and delta P solvent represents the change in the vapor pressure of the solvent. And it's going to be the mole fraction of solute multiplied by the P naught of the solvent. And the P naught of the solvent is the vapor pressure of the pure solvent, which is given to us over here. You'll also notice that a temperature is provided as well. The temperature actually does not figure into the problem. The reason the temperature is there is because the temperature, well, the vapor pressure is temperature dependent. The higher the temperature is, the more the vapor pressure is. So we have to quote a vapor pressure at a specific temperature, but we don't use the temperature in the problem. So delta P solvent is the mole fraction of the solute, which is 0.079. We get that from up here. Here's the mole fraction we calculated here, which was moles of phenol over moles of phenol plus the moles of acetic acid. Came out to be 0.079. So it's going to be 0.079, which doesn't have a unit, by the way, times 20.0 torr. So the 1.6 torr represents the change in vapor pressure that is represented by this mole fraction of solute. To get the new vapor pressure, we take the pure vapor pressure, which again we were given up here, and subtract out the delta P of the solvent, which gives us 18.4 torr. Does anybody have any questions about vapor pressure lowering? Okay, how do you feel about vapor pressure lowering? How do you feel about vapor pressure lowering? Five, four, three, two, one. Okay. Questions? A few people who don't quite get it, so. Questions? All right. The last one is osmotic pressure, and osmotic pressure has the formula big pi, that's the osmotic pressure, equals mRT. Now, M is going to be the molarity. R is going to be the real gas constant, which is also going to be given to you. You don't have to memorize that. 0.08206 litres atmospheres per mole per Kelvin. And then we've got the temperature. The temperature is in Kelvin, and you can see it's 25 plus 273. That gives the 298. The 1.2 moles per litre comes from the molarity that we calculated up here. Molarity of phenol, which was 1.2 moles per litre. And then that gets multiplied by the R and the T value, of course, and that gives us 29 atmospheres. So as you can see, that's a pretty big pressure. I mean, that's 29 times atmospheric pressure. So one of the other applications of osmosis is something called reverse osmosis. Now, reverse osmosis is what happens if you put pressure that's more than the osmotic pressure. In this case, it'd be 29 atmospheres. If you were to put that on the piston, what could happen is, remember, there's solvent and solute on this side of the semi-permeable membrane. But if you were to push enough pressure on this specific piston that it would exceed the osmotic pressure, then you could push pure solvent back behind the semi-permeable membrane. And this would be a method that you could use to actually purify water. So this is actually done. The problem is it takes a lot of energy, and also it takes a lot of filtration as well, because the reverse osmosis, the semi-permeable membranes tend to get covered in stuff, which isn't great. So that's technology, I think, that still needs a bit of work, but there have been reverse osmosis plants built to actually purify seawater. And that's the principle that they're using there. Does anybody have any questions about osmotic pressure? All right, I'll just say one more thing about osmotic pressure. If you look at the formula, it might look a little familiar, because if you've got gases, remember we have this formula PV equals nRT. And if you were to take the formula and then rearrange it a little bit, make it N over V. N over V is effectively concentration. It's moles over volume. Molarity, which is where the molarity comes into play. Now, I know this is for gases, this is for liquids, but the same thing kind of applies. All right, does anybody have any questions? Okay, let's see. How do you feel? How do you feel about osmosis? Osmotic pressure. Okay. Any questions? Any questions? All right. Now, another part of this is something called the Vant Hof Factor. And if you'll remember, the colligative properties have to do with the number of particles. So this is a correcting factor, if you will, and we call it I, and it goes simply in front of all the calculations we've just looked at. So it's I KFM, I KBM, I chi solute, P naught solvent, pi equals I MRT. We only use the Vant Hof factor when we're dealing with ionic solutions. And what we're trying to do there is just take into account the number of particles we're getting from that ionic solution. And what that means is we have, so Na2CO3, for example, that would be I equals 3 because there are 2 NAs, Na pluses, and 1 carbonate. AlCl3 would be 1 aluminum and 3 chlorides, that would be I equals 4, and HBr would be H plus and Br minus, which means I equals 2. So that's how we deal with ionic solutions specifically when we're dealing with that. What I can tell you is the Vant Hof factor is not something that I actually put in the actual test, but it is something that is part of the fun quizzes. So that's why I include it here as well. All right, does anybody have any questions about the Vant Hof factor and calculating it? Okay. So let's look at the test now, and I'll show you what kinds of things you're going to be dealing with on the test. Okay. So we've got these questions here, 25 through 28. These are all concentration questions. As you can see, you've got a mass percent question where X ends up being the solute here. And you're also given a Y as well, which could be in a volume or it could be a mass. But if it's a volume, then you would need to convert that into a mass by using this formula, density times volume. And this is already given as a mass, so you can see how you would do that. The next question here is a molarity question. And for this, you would need to be a little bit sensitive to whether it was a solid or a liquid. If it's a solid, I will say it's a solid. If it's a liquid, it'll be fairly obvious because a density will be provided as well. So if it's a solid, it will say so. Otherwise, you're going to have to assume it's a liquid. And then you can go from there. You can see that here, it's going to be density 0.897 grams per mil. The other thing that gives it away is the fact that you are given a volume. If it was a volume, it would never be considered a solid anyway. Does anybody have any questions about that? Okay, the next one is molality. So you're expected to find the molality of this solute. And the next one is mole fraction, but again, it's mole fraction of just the solute here. The colligative properties, you're given all of these formulas here to help you out, along with the R value. Now, these don't include the Vant Hof factor because all of these are not things they split into one particle. They're single particle species. They're not ionic, so we don't have to worry about the Vant Hof factor here for any of these. In most of these cases, it's a matter of calculating the molality first. For this one, calculating the molality first, and then using the formula here to find the change in freezing point, which is then applied to the new freezing point here, or the pure freezing point, to get the new freezing point at the end. So we use freezing point depression again in that case. In the next one, we're given a mixture again of X and Y, and again we have to find the molality and then calculate the new boiling point. Vapor pressure lowering, we have to do the same thing, and osmotic pressure. So those are all of the questions that relate to concentrations and colligative properties that you'll see on the test. So obviously the best way to study for these is to do them, is to continually do them on the test. So it's going to be pretty much the same questions. Whether it's a solid or a liquid will change. The kinds of calculations are going to be pretty much the same for all of them. Does anybody have any questions about what they're going to see on the test here? Does anybody have any questions of what they're going to see on the test? Okay. All right, let me say a little bit about, I have to get out of here. Let me say a little bit about the fun quizzes here. Remember, these quizzes are extra credit, just like they were for test 3. You don't have to do them, but they can help boost your grade. Now, I believe your test 4 is going to be due next Monday. There's also the test 4 units quiz as well that you'll need to do. It's part of your grade. Let me preview the test 4 units quiz for you. You're not going to like it very much, I must admit, but this is how it works. Let me show you what it looks like. So the idea here is that it's not about the numbers, it's about the units. So if you need to match the units to the setup below. And for example, this would be for molarity of X. So the final thing you want here is moles per liter or molarity, depending on what's here. It says mole X per liter, that'll be the final one. So that would go, that's what 7 would be, because that's molarity. And here, if you're looking for molarity, then you need moles on top. So 1 must be 1 mole. And 2 must be the molecular weight of X. There it is. That's the molecular weight. So that's going to be 2. Down here, we need the total volume. So we need a volume here. So 3 must be a volume. That'll be milliliters of X. And that'll be the density, d grams of X, number 4. And then times 1 liter over 1,000 mils. That's 5 and 6. 5, and 6. And the 1,000 litres is unused, so you put an 8 next to that. There you go. All right, I'm going to ask how you feel about this. I think some of you won't feel very good about it. That's my prediction. Let's have a look. How do you feel about it? Five, 4, 3, 2, 1. Still, somebody doesn't like to vote here. So as you can see, there are a couple of people who don't understand anything here, what's going on, but that's okay. You'll practice it and then you'll be okay with it. Does anybody have any questions? If some people there don't understand it at all, I think you've got to ask questions. Right, we'll just read the directions here. It tells you what everything is here and what you need to do. Okay, if nobody's going to ask questions, you'll see this is what you have to do. All right. All right, does anybody have anything else that they wanted to ask about so far?
So for that problem, we're just finding anything that's missing.
Yeah, whatever that fits, fill in the blanks. That's what it is.
Okay.
So there is a expressing concentration quiz here. And I also have some videos here for some of the harder problems that are part of that quiz. Remember, these quizzes are extra credit. I'm not really wanting to go through them in class because they're extra credit. There's also a Colligative Properties practice quiz and credit quiz as well, and solubility of gases in liquids I told you about earlier, which is based on the PowerPoint notes. There's no video for that or anything, but again, this is all extra credit here. Does anybody have any questions?
So some of the quizzes will be on the PowerPoint.
Yes.
Thank you.
Does anybody have any other questions? All right. Well, I think we'll leave it there. If you have any questions, let me know. We have just one other thing to cover, and that's heating curves. And then we'll do a little bit of review, but I would strongly recommend that you get started on this practice test. Don't leave it till last minute, because otherwise, you will run out of time. And everybody, if they put the time in, they can get through it. But the question is, are you willing to put the time in? That's what it comes down to. All right, well, that's it. And I'll see you later on. If anybody wants to hang around and talk to me, they can.
Bye, Professor.
All right, see you later.
Thank you, Professor.